Alrighty, I think we looked at this one in class, but let's see. State and explain the nature of the particle labeled X, right? So this is electron capture, right? So notice on this branch we've got a perfectly good electron that's going away, right? So in order to capture the lepton number for this thing, right, this thing has to have. Notice that the proton, the positive charge, comes out here, right? But a positive and a negative would be what? What's the charge on that, right? So Q for that guy is going to be 0, but it's got to have an lepton number of positive 1. And there's only one thing that doesn't have charge but has a lepton number of 1, okay? So state and explain the nature of it, right? So explain all that, right? It has to be neutral, right? It carries a lepton number, therefore it must be a blank. Okay. Distinguish between hadrons and leptons. Well, hadrons start with the letter H, right? Remember, the leptons are fundamental particles, right? Hadrons are made of quarks. There's all kinds of things, right? But, come up with your own differences between hadrons and leptons. Hadrons are things like mesons and baryons, right? Leptons are things like the electron neutrino, the muon, the mu neutrino. These are leptons. The tau and the tau neutrino, right? These are all the fundamental particles that are leptons, and then there's hundreds and hundreds of different hadrons, right? All right. Okay, so let's see. Particles can be used in scattering experiments to estimate nuclear sizes. This was a vague question. So when you look at the mark scheme, you have to let me know what you think. Right? There's basically like 3 different possible things. I was thinking about the classic Rutherford experiment where you've got this, thin film of stuff. You've got alpha particles, right? Flying this way, right? And then you have a detector out here. And you detect the angle through which the scattering occurs, right? But there's another way to do it too, which is kind of cool, and that is that you actually treat the gaps between the atoms as little gaps that, and you accelerate electrons in this case up to a high velocity, right? So that they have a really small wavelength. Remember, the wavelength of them is what Planck's constant over their momentum, right? So you make them have a de Broglie wavelength that's similar to the spacing between the atoms, right? Like 10 to the minus 15th or so, like that, right? And then you can actually get a diffraction pattern, and from that diffraction pattern, from the angular distribution of it, and you'll see there's a question that we're going to do later. You can determine the spacing of the or the size of the nuclei, right? Okay, so explain how they're carried out. Talk about this, right? How you're analyzing you're analyzing the distribution of the scattering angle, right? And I just sort of BS'd my way into 2 marks. Let's see if you can do that too, right? Why do they have to have high energies? Well, there's 2 different scenarios here, right? Here you want a high energy so they can get close to the nucleus, right? The closer you can get, the better you can determine the nuclear radius, right? Because you're getting close to it, right? Okay. In this case, you actually want a high velocity so that you have a short wavelength, right? The shorter the wavelength, the better the resolution, right? State and explain one example of a scientific analogy. There's no non sequitur here. It's not related to this. Just come up with some analogy, right? Like we talk about like when we leave Earth, it's like we're climbing out of a gravity well. It's like climbing a hill, right? And we made an analogy. Remember when we made we talked about the equipotential lines, how those were like walking on a contour line on a topological map, and how the electric field was like the fall line perpendicular to that. Anyway, that's an analogy, right? It's not the same thing as, but there it is. It's an analogy. Let's see. Electron diffraction experiments indicate that the nuclear radius of carbon is about 2.7 times 10 to the minus 15th. The graph shows the variation of nuclear radius with nucleon number. The nuclear radius of the carbon-12 is shown on the graph. Determine the radius of the magnesium-24 nucleus. It was like 2 marks. Right? Well, I just used, whoops, I just used the formula for the radius of an atom, right? R naught, A to the 1/3, right? Maybe we're supposed to use, like, read the graph and use that thing, right? Let's see what it is. D, correctly plotted. Let's see. Oh, okay. Allow the use of the Fermi radius from the data booklet, right? All right. And I got something that was within the range, right? Here's what they say you're supposed to do. They say that it's, so the radius here is about 2.7, right? 2, 2.2, 2.4, 2.6, 2.7, right? 2.7 times 10 to the minus 15th, right? Okay. Notice that this is carbon 12, so it's got 12 nucleons. Here it's 24. Right, and so it would be this times 2 to the 1/3, right? Okay, I just used this and I got full marks. So they were like, determine the radius of it. If they give a formula, it's kind of funny, right? They should have said, using data from the graph, determine the radius of the nucleus, right? But, you know, there it is, right? Plot the position of magnesium-24 on the graph. So go here, plot what that new radius is, right? I got, by the way, somewhere between 3 and 4 times 10 to the minus 15th meters. So plot that thing there, right? And then draw a line on the graph to show the variation of nuclear radius with nucleon number, right? Well, I didn't guess. I just sat there and, you know, did different nucleon numbers, right? What's interesting to me, though, is that the graph that I made very carefully by just plotting points. So for example, try 6. Do 6, do 18, do 30, do 36, right? Okay. And then do some of the ones in here too. Do like 3 as well, right? 3 would be right there. What's interesting to me is that the graph they give you on the mark scheme is just plain wrong. Plus they make it go to 0. Like, well, yeah. I don't get it, right? The smallest nuclear radius would be 1.2 times 10 to the minus 15. And beyond that, it's not a nucleus. But anyway, they make it go through 0, which I think is just stupid. All right, so yeah, go ahead and see if you can graph that, right? You know, if they ask you to estimate a graph, but they give you numbers, well, don't estimate, just graph it, right? You can even use the graphing function on your calculator. All right.